Chapter 15, Multiple Integrals. Section 15.1, Double Integrals over Rectangles. So before we start this section, let me just review where we have been and see where we are going to be going. Okay, so where were we? So suppose I have the graph of some function. Let's say, I guess some function here, y equal f of x. Then the derivative is the best linear approximation to a function near some point. We had, well, for a function of one variable, if we are at some point A, then in some distance h from A, then the change in f as a function of how far you are away from A can be approximated by the differential of f at A at a distance of h from A, and the error in the approximation we want to be small, little o of h. If it is, then we say that the function is differentiable at A. So if the change in f at A evaluated at h is the differential of f at A evaluated at h plus little o of h. And basically the first half of this course and trying to extend this idea to functions of more than one variable, that and maybe several functions, that the change in f at A of value at h is just the differential of f at A value at h plus little o of h. So that was our concept of the differential, and we did a whole bunch of work trying to realize what that definition meant. So now, where do we want to go? Well, we want to look at not only derivatives, but integrals. And so in the first variable case, suppose I have y equal f of x, and suppose I have some endpoints a and b. In this case, I'll assume that they're finite. They don't obviously have to be, but I'll just say a and b. Then the area under the curve is just the integral from a to b of f of x. And, well, if you recall, there was a relationship, the derivative and the antiderivative, the integral. We had that the integral from a to b of f prime was just f of x evaluated at b and a. So we want to extend this idea to functions of more than one variable. I can write this as the integral over the interval ab of, well, the differential of f, which is just f prime dx, is equal to, well, f evaluated on the boundary. So eventually, we want to extend this to the idea that it's the integral. Oh, what do I want to call it? Let's call this omega. And I'll call this form omega. And so rather than saying the integral, maybe I'll extend it to some region, capital omega. And I have some differential form is equal to, well, I can give this as a weird notation. I'll say, well, evaluation on a boundary, I'll just call that evaluation on a boundary of this form. And so we'll try to extend this idea of the fundamental theorem of calculus to having more than one variable. And this is sort of our goal, is to extend this idea of the fundamental theorem of calculus to somehow functions of more than one variable. Okay, so before I can do that, I need notation. So I partition. I partition P of a closed interval A to B, so I have this closed interval A to B, is any decomposition of the, let me just move this up slightly. Well, I guess not. Let me move this up just slightly. I don't like the way it's looking. Okay, just a hair bit higher. Okay, so somehow that didn't move it. So a partition P, so this is my partition, of a closed interval AB is any decomposition of the closed interval AB into subintervals. So these will be some subintervals here of the form, well, x0 to x1, x1 to x2, x2 to x3, dot, 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 xn minus 1 to xn. For any positive integer n, these numbers x0, x1, dot, 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 to xn are such that x0 is equal to a, x0 is less than x1, which is less than x2, which is less than x3, dot, 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 which is less than xn, which is equal to b. And so my partition is just this set of points. The width of the subinterval. So the width of my subinterval, the width of the kth subinterval is denoted by delta x sub k, and is defined as x sub k minus x sub k minus 1. So let's look here at the partition of my interval AB into points x0 through xn. Then x sub 1, delta x sub 1, is just x1 minus x0. It's just this length of this first subinterval. Delta x2 is just x2 minus x1. It is the width of this second subinterval. Delta x3 is just x3 minus x2. It is the width of this third subinterval, etc. The norm, or the mesh of the partition, is defined as follows. The norm of the partition P is denoted by the norm of P, and it's just equal to the sup of delta x sub k. It is the largest of all these, of all the widths of the particular partition. So for this partition, what is the biggest, what is the width, the biggest width for any of these subintervals? So it's a sup for k going from 1 to n, where k is an integer and where x sub k is in your partition. So it's the largest in your partition of any of the subintervals in your partition. The Riemann sum. Okay, so f of x, so let's say this is y equal f of x. So let f be defined on the closed interval a to b. So f here is defined on the closed interval a to b. And let P be a partition of the closed interval a to b. So I have some partition here of this closed interval from a to b. A Riemann sum of f for the partition P and choice points W. So I have some choice points W. These choice points W are, well, the kth choice point is any point in the closed interval, in the kth closed subinterval, as determined by the partition P. So the Riemann sum, W some point in the closed interval from x0 to x1. W2 is some point in the closed interval from x1 to x2, etc. A Riemann sum of f for a partition P and choice points W, denoted by R for Riemann sum, P comma W for the partition and for the choice points of f for the function, is an expression of the following form. It is the sum from k equaling 1 to n is determined by your partition, f of W sub k, where the W's are your choice points, as in your partition, delta x sub k, again, those are the widths of each of the subintervals as determined by that partition. So again, where the W sub k's are in the closed interval from x sub k minus 1 to x sub k for k equaling 1 to n. Riemann integrability. Let f be defined on a closed interval a to b if there is a real number, and we'll denote this real number a to b, f of x dx, such that for every epsilon greater than 0, there's a delta greater than 0, such that if P is a partition of the closed interval AB with the norm of the partition being less than delta, implying that the absolute value of the difference between the Riemann sum and this definite integral is less than epsilon. For any choice numbers, delta W sub k of the partition P, then F is called Riemann integrable. Again, I'm just restating this, where W sub k is in this set of choice points for the partition P, and these choice points consist of these n numbers where the kth choice point is in between x sub k minus 1 and x sub k, and it could equal any of either of these two endpoints for k equaling 1 to n, where x sub k is in the partition of the interval, the AB. Okay, lower Darboux sum. Let P be a partition of AB, the closed interval AB. Let M sub I be the mth of f of x for x being between x sub I and x sub I minus 1. You know what? I wrote that in the wrong order. Because x sub I minus 1 is less than x sub I. Okay, xi minus 1 comma xi. Not that it really matters. Um, so, uh, so m sub I is the nth. It's the sum of f in the ith subinterval. So m sub I is the smallest value of f in the ith subinterval. Then L sub p of f I equal 1 to n of m sub I delta x sub I. And this is called the lower Darboux sum. The upper Darboux sum, well, it's defined just about, oops, of course I made the same mistake. Okay, let P be a partition of the closed interval AB. Let capital M sub I equal the sup of f of x for x between x sub I minus 1 and x sub I. So m sub I is the largest value of f in the ith subinterval. Then u sub p f is equal to the sum, I equal 1 to n, m sub I. Let's see if I can see what the question is. What is the sup? Oh, the sup. Sure. So the sup in mth. I'll just have to sort of put it here. So the sup is the supremum, or maybe I'll write it over here since I have some room. The sup is the supremum. Supremum. I think that's how you spell it. It is the greatest lower bound. It's the smallest. Think of it as just being, greatest. Supremum is the, I wrote the wrong one. It is the least upper bound. It's the biggest number. Supremum is the maximum. It's the least upper bound. So if you just think of it being the maximum. So sup, so it's more or less the maximum. And the infinum, oh, that's completely wrong. Infinum. I don't know how to spell that. Yeah, whatever. Spelling is wrong. Infimum. Well, okay. It is spelled something. I certainly know this is an incorrect spelling. It is the greatest lower bound. Lower bound. Yeah, think of this as being the minimum. Oh, I see. I put, that was the inf, that was, well, whatever. I put in the wrong order. This was talking about the sup here. Okay. And this was talking about the inf. Okay. So just think of, and again, wrong spelling. I certainly know this is a wrong spelling. But I don't know how to spell it. Okay, so is that clear? Okay, so let me do Darboux integrability. Okay, so let me just see if I can Oh, infimum. Okay, that's how you spell it. Infimum I. Sorry, I had to look it up because I did have an I there. It didn't look correct, but doesn't matter. Okay, infimum. Femum. Yes, okay, that's how you spell it. And supremum. Okay, sorry. I just wanted to check spelling. Okay, so Darboux integrability. Let f be defined on the closed interval AB if there is a unique real number, the definite integral from a to b, f of x dx, such that for every partition P, the number, which we denoted by the obvious symbol, the integral from a to b f of x, is between the lower Darboux sum and the upper Darboux sum for every partition P, then f is said to be Darboux integrable on the closed interval. It turns out that this definition of Darboux integrability is much easier to check than Riemann integrability, and it's just much easier to do proof for anything else. Note, f is Riemann integrable if and only if f is Darboux integrable. So that these two concepts are the same, so usually we introduce both of them, and eventually, after you have a little bit of practice, we just stop talking about Darboux integrability and just deal with the Riemann integral. Oh, also, sometimes I use this notation. So let P be a partition of the closed interval AB. Define the length of P to be n if the partition P consists of x0, x1, x2, dot, 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 x sub n. This just tells you the number of subintervals determined by your partition P. Okay, so that was a review of what you did back in Calculus 1. Now let's try to extend this idea to dealing with, instead of one variable, let's first just deal with two variables. So let's just look at two variables. Once you end it to n variables. So partition of a closed interval, a closed rectangle, R, which consists of the Cartesian product of the closed interval AB with the closed interval CD. Let P sub x be a partition of the closed interval AB, and let P sub y be a partition of the closed interval CD that we defined above. Let x sub I, oh, how do I want to call that? Let this be in your partition. Well, you can either do it as a closed interval, or let x sub I minus 1 to x sub I be a closed interval by this partition in X. Let the closed interval y sub j minus 1 to y sub j be a closed interval as determined by this partition of y. And let R sub ij be the Cartesian product of this closed interval from x sub I minus 1 to xi with the closed interval y sub j minus 1 to y sub j. Let delta r sub ij equal. So notice that this was r sub ij is just a rectangle, the Cartesian product of these two closed intervals. Let delta sub ij, delta r sub ij, well, that's just going to be, instead of a length, it'll be a two-dimensional length, meaning an area of a rectangle. And so I just want to do the area of a rectangle, length times width. And so delta r sub ij is equal to the product of x sub I minus x sub I minus 1 times minus x sub j minus 1. Let w equal w sub 1 1 comma w sub 1 2 dot 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 w sub mn, where the number of partitions of subintervals in the partition of x is m, and the number of subintervals of the partition in y is n, where each of these w sub ij jth rectangle. So we've partitioned up the R2 into a whole bunch of rectangles. In the ith jth one, I want w to be in the ith jth rectangle. So you have some ij rectangle, and w ij will be in this ijth rectangle. Okay, so let f be a function from R2 to R. Let m sub ij equal the mth of f of x. Well, maybe I should call it xy, but f of xy, where xy is in the ijth rectangle, and m sub capital M sub ij be the sup of f of xy for the point xy being in the ith jth rectangle. Let P, the partition P sub xy, be the Cartesian product of the partition of x cross the partition of y. Let the norm of this partition in the, well, both x and y variables be the sup over I and j of delta r sub ij. Let the lower Darboux sum L with respect to the partition of the variables in the equal the sum over I and j of m sub ij delta r sub ij. Here, this is really is a double summation. You're going from one to I, let's see, which is this is x, 1 to m, and j going from 1 to n. Let the upper Darboux sum with respect to the partition of the variables in the variables x and y of f equal, again, the double sum over I and j of capital M sub ij delta r sub ij. So you notice that they're very similar to the upper and lower sums that we defined 2 minutes ago. First, let me define Riemann integrability. A Riemann integrability is, again, a little bit more difficult concept of Darboux integrability, because you not only have a partition, but you also have, so a partition gives you an infinite number of things to look at, but within that you also have an infinite number of choice points. So it's an infinity of an infinity. So it makes it a little bit more difficult to see what's going on, but let's do this. So let F be defined on R and some rectangle R, and if the real number by the double integral over R of f of x, y exists such that for every epsilon greater than 0, there is a delta greater than 0, such that the norm of the partition in the variables x and y implies that the absolute value of the difference between this Riemann sum, the double sum over I and j, of f evaluated at w ij times delta r ij minus this double integral, this definite integral of the double integral over r of f is less than epsilon. And this is true for any wij in choice points w relative to some partition p. Then f is Riemann integrable over r. Darboux integrability over r. If there exists a unique real number, again, we denote it by, well, the thing we always want to denote by the double integral over r of f, such that, oh, and then sometimes I'll be replacing this d of a by things like dx, dy, or something. Such that for every variables x and y of r, this number, the double integral over r of f, is between the lower Darboux sum and the upper Darboux sum for every partition p. Then f is said to be Darboux integrable over r. In other words, f is Darboux integrable over r if for every epsilon greater than 0, there exists a partition p of x, y, such that the upper Darboux sum minus the lower Darboux sum is less than epsilon. A set of measures 0. Let B be some subset of R. Let f of x, y equal 1 if x is in B, and let it be 0 if x, y is not in B. And so if you have some so then we say that B has measure 0 if this number that we just defined above is equal, its integral is equal to 0. And so if we happen to have some set and we look at the integral above it, where it just value 1, if it's in the set and 0 outside, meaning I'm just looking at the area of this region. If the area of this region is 0, then we say that it has measure 0. So that's the concept of measure 0. volume. The volume of F above R. Oh, and I guess I should have said this, even though I didn't say it in this case. Case, Darboux integrability and Riemann integrability are the same. And so a function is Riemann integrable if and only if it is Darboux integrable. Okay, so the volume of F above R. Ooh. And so if F of xy is greater than or equal to 0 for all xy not in B, where B has measure 0, then the volume of V of solid that lies above the rectangle R and below the surface z equaling f of xy is defined by the double integral of f with respect to dA over the region R. And so the volume of F, just like the area under the curve, of course, so if F is non-negative, like in the one-dimensional case, then the area under the curve is just given by the integral. Okay. Now, if I happen to look at a function of more than one variable, I don't know if I can do this, but over some, so it's some sort of, here's some rectangle, I'm trying to draw it. Here's some rectangle R, and here's some function above it. There, okay, so it looks like some function above it. Okay, then the volume, V, is just, so this is some, let's call it Z equaling f of xy. Then the area, the volume under this curve is just given by the integral. Fubini's theorem. So, Fubini's theorem says the following. If the double integral over the Cartesian product of x and y of the absolute value of f is less than infinity, then the double integral over the Cartesian product of x and y of f is the same as the following, the iterated integrals. The integral of f of xy integrated with respect to y, and then integrated with respect to x over the sets x and y, which is the same as the integral of f with respect to x over the region capital X, then integrated with respect to y over the rectangle, over the interval y, over the set y, capital Y. Okay, so if f is continuous on a rectangle, R being the closed intervals from AB, Cartesian product with the closed interval CD, except on a set of measures 0. So it's continuous everywhere except for a few points. And those points only accumulate to something having no volume, no area, and so it really doesn't make a difference in this integration. And so because it doesn't really make a difference, we can disregard it. It's like if I had a function that looked like this, then the area under this curve is still this, even though I've got one hole here. So the fact that it has a hole, maybe it's defined up here as some weird value, it doesn't really matter. It's continuous everywhere except for maybe a few points. Maybe it looks like this. Then it still is the area under that curve. So as long as it's continuous, except for a few points, and those few points don't make a big difference, meaning they only have measure 0, then the integral over R of f of xy, integral from c to d of f of xy, first integrating with respect to y, then with respect to x, integral of f from a to b, integrating with respect to x, and then integrating from with respect to y from c to d. So you can do it in either order. And so it means that taking this integral is actually very easy because you just do, you integrate just like you would in the one-dimensional case that you did in calculus 1. It's just in this case, you're going to fix a variable and you keep integrating until you don't have any other integrals to do. And you'll be then evaluating at some endpoints. Average value of f over region R. If you recall, the average value of a function over some closed interval AB was just, oh, and I guess I should have said that. Maybe I'll say that here. The average value in the one-dimensional case was the integral over the region AB of f divided by b minus a, which is just the length of the interval AB. And so it's the integral over some interval divided by the length of that interval. And so in the two-dimensional case, the average is just the integral of f over this region R divided by the area of the region R, which is what we had from above. Approximations. So by Fubini's theorem, we can use the approximation rules that we had for calculus 1. Oh, and I guess they were actually in calculus 2, that you saw in calculus 1 and in calculus 2. We can use those same approximation rules and the fact that assuming that the Fubini's theorem works, we can then just do these approximations on the iterated integrals and get an approximation formula for functions of more than one variable when we're integrating over those functions. So first, the midpoint rule. So the integral, the double integral of f of xy over the region R is just the sum over I and j of f of x sub I bar, y sub I bar, where x sub I bar, y sub I bar is the midpoint, the middle of the ith j rectangle times delta r sub ij. And this is going to be correct up to little o of the square of the mesh of your partition. The trapezoidal rule. So the trapezoidal rule says that, well, the double integral over R of f is, well, as long as Fubini's theorem holds, I'm just assuming, in order for us to do this approximation, I'm assuming Fubini's theorem holds, the integral of f of xy with respect to y integrating from that with respect to x from a to b is just, well, I guess I'm going to derive it, is the integral from a to b with respect to x of, well, you use the trapezoidal rule. So the trapezoidal rule is just the sum j equal 1 to n of 1/2 f of x, let's say y j minus 1 plus f of x yj. Okay. And so you can put the integral inside. So this is 1/2 sum j equals 1 to n delta x of j. I'll just bring that out. Integral from a to b of f of x y sub j minus 1. Again, integrating with respect to x plus, well, these have all the same terms, so I don't have to worry about that, plus integral from a to b f of x comma y sub j, plus little o of the square of the mesh for this particular partition. So this is equal to, well, I can use the trapezoidal rule on this guy and the trapezoidal rule for this guy. So this is equal to 1/2 sum j equal 1 to n delta. And now let's do trapezoidal rule for, in this case, the x's. So this is going to be 1/2 sum, this went to n, so this goes to m, sum I equaling 1 to m of, well, I guess I'll put it here, delta x sub I. This will be f of x sub I minus 1, j minus 1 plus f of x sub I, then y sub j minus 1. Plus, now let's do it for this guy. So again, this is going to be 1/2 sum I equaling 1 to m delta x sub I, f of x sub I minus 1 yj, plus your little o of the square of the norm of your partition. So, half sum j equal 1 to n, I equal 1 to m of delta xi, delta xj. This is going to be f xi minus 1, j minus 1 plus f xi yj minus 1 plus, let's see, these are all the same because this is, yes, this is the same. So this will still be in the same summation, double summation. F of xi minus 1 yj plus f sub I y sub j plus little o. So this is the trapezoidal rule. Oh, I wanted to rewrite that. Okay, so okay, so I don't know if it's 15 minutes to go over that. This is just a rewriting of this. Okay, so so I peeled off the, so if you remember, the trapezoidal rule looked like a 1, 4, 2, 4, 2, 2, 4, 1 pattern. And so to do that, we in the one-dimensional case, besides just taking these and averaging them, what we did is we did this was a 1, 2, and then and so then we averaged these guys, and when we did this, when we regrouped everything, we got this. So I guess it's 1. So we regrouped them, and we got that pattern. Okay, so now let's do it for this guy. Okay, so let's peel off the first term. Okay, and then plus, and so now let's just look. So let's just look at when I equals 1. So when I equal 1, let me peel off the very first term here, and then this is the rest of the sum. Next, let's look at when j is equal to 1. So now let's look here when j equals 1, and let's peel off when j is 1. Okay. Next, for this guy, do the same thing. Okay. And for this one, so you're going to again, here, for this one, I guess I'm going to look at the case where I'm here at x of m. So I look at the endpoints. So you just look at the first point and at the last point. So just look at the first point and the last point, peel those off, because you know those are going to be ones. They're going to be 4 of them, and they'll just peel off. Then look at every other one, and that's what I'm doing. Regroup. So I'll just a whole bunch of algebra. Okay, so regroup, and you finally get this. So you can go through all the little algebra. I'll just say the algebra is there. It's just you peel off the first few terms, you peel off the terms, you regroup everything, and you get delta x, delta y over 4. These are the corner points, plus 2 times every other, all the points on the little endpoints, plus 4 times the guys in the middle, plus little o of this partition, the norm of the partition squared. So let's look at this visually. It's easier to see it this way. So what is What is the trapezoidal rule? So if I look here at a mesh, and let's look at the ith member of this partition. So at the endpoints, so if you recall, the pattern for the one-dimensional case for just having a integral with one variable, the pattern was 1, 4, 2, 4, 2, etc. Okay, which we somehow, I guess it was this pattern that we just sort of kept repeating over and over again. 1, 4, 1. I'm sorry. There's a 1, 4, 1 pattern that we kept repeating. Okay, and we just sort of re-added up everything. Okay, so now if I look at this, so it's a 1, 4. That's a one-dimensional case. Now, rather than having these two endpoints having a value of 1, we have 4 corners. So the 4 corners of our rectangle will have a value of 1 in the trapezoidal rule. Whereas the guys in the middle that are not on any of the sides will have a value of 4. Whereas the guys here on the sides that are not will have a value of 2. So that's how the pattern goes. That's how you extend this. Okay, so of course I didn't finish this guy yet. This is 2i, oops, 2i, 2j. Minus 1. 2j minus 1. That's a 2. And that's a 2j. Okay, so I don't even know if I want to. So this is actually after it's been simplified. So this is Simpsons rule. Infimum, yes. Okay, infimum. Oh, but someone's going to type something in, I think. No? Okay, so I'll just sort of leave it. Well, okay, maybe it just took a while for this to come up. Okay, so Simpsons rule set for two-dimensional case. Integral over the region R, rectangle R of F, delta X, delta Y over 9 times. For the corners, you're going to just be multiplying by 1. So there, and I'll just sort of point to this. There are 4 corners and have 1s. Then on the sides, so here, so this is a typo. Okay, good. Okay, so this term here says that this side here goes just like how you did in one-dimensional case. 1, 4, 2, 4, 2, 4, 2, etc. 4 and then 1. So it keeps alternating with the 4 2s. This says, 2m. That says that on this side, we also alternate just like what we did, 1, 4, 2, 4, 2, 4, 2, and then eventually a 1. So that's what this guy says. This one, this is the 0. Okay, this says if I look here at the bottom, it also alternates 1, then 4, 2, 4, 2, 4, 2, 4, 2, and then, okay. This guy here is the top. So that says that this also alternates. Has 1s at the corners, which we already dealt with, but then it alternates 4, 2, 4, 2, 4, 2. So that was this last one. Now this says we have a whole bunch of 16s. So we have 16s in the every other square. So if you, they have a 16 here, 16 here, 16. So every other square has a 16 in it. That's what this says here. And this says here that they keep alternating between 8s and 16s and between 8s and 4s. Okay. And that's what this pattern is. So that's what this last thing says. Okay. I think I wrote it correctly. Yes, okay. And that's the alternating. Okay, so got 5 minutes. Let's do problem number 6 on page 1039. A 20-foot by 30-foot swimming pool is filled with water. The depth is measured by 5-foot intervals starting at one corner of the pool, and the values are recorded in the pool. Estimate the volume of the water in the pool. And so, let me actually insert something. Okay, so let's use the rectangular rule, trapezoidal rule, sorry. Let's use the trapezoidal rule. And so the trapezoidal rule, which we just did, oh, a lot. So the trapezoidal rule says something like this. But I'm actually going to draw yes. Oh, why? What's the, so the problem is, so why are we using trapezoidal? Because we don't have anything else to use. So if I look at this, it doesn't give me a function. So if I just said, let's say in the one-dimensional case, if I said the, f of x, if I just gave you x and y, 0, 3, 4, 2, 6, 5, and I say, okay, approximate the area under that curve. Well, the problem is you don't have a curve, right? You only have some points. And so the only way to approximate, the only way to find the area under that function would be to do an approximation. And you could figure out which approximation you wanted to use. Obviously, Simpsons would be a better approximation, but, and they also say estimate. So the thing is, we don't have a function, so we can't integrate. because there's no function to integrate over. And so I can only do an approximation. Okay, is that clear? So that's, I'm sort of stuck because I don't have anything else to do. And so this is my trapezoidal rule. Now I'm going to actually not use this. I'm going to use a picture instead. So this is my rule, but it's not as convenient as the picture. So we're here. Oops. I hope I didn't erase anything. Yeah, whatever. Okay. Okay. In this case. Okay. So the real thing that I should be using, so in this case, I guess, well, delta x and delta y, notice that these are always a distance of 5 apart. So I can figure out delta x and delta y. And then each of these points in the grid are going to tell you what the value of the function is. Okay, so let me copy, because I already did it. Let me copy this picture, because the picture is worth 1,000 points. And so it's so much easier than actually the formula. So rather, let's just do the picture and figure it out from there. So my picture is this. Okay, so so the volume, which is actually it is a double integral, but we don't know what the function is. So the volume is approximately, well, the only thing I need from here is this factor, which is delta x, delta y. Well, I said delta x, I don't know, maybe I'll call this x and this y. The delta x was 5, and the delta y was also 5. By the way, I'm assuming, just to make the formula so much easier, I'm assuming that we have a regular partition. So the deltas are always the same for each subinterval. So that this is 1/5 for each of these. So 5, 5, and 4. Okay, so now at the endpoints, we have a 1. So we have 4 endpoints, 1, 2, 3, 4. Okay, maybe I'll mark these. So, okay, sorry. Why is it not? Okay, so let's do that. So this, 4 points here, are these 4 points there. And they just have a value of 1. So I just add them. So I'm just going to say, and then that's these 4 points. Oops, that's these 4 points here. Okay, so I'm just going to be adding these 4 points. 2, 2, 8, and 4. Okay. Next, let's do. Maybe I'll do it in orange. I'll do these. Okay, these guys here. And so these will have a value of 2. I'll multiply everything by 2 here. This, and then I don't know how to. So these guys here. I'll be taking each of those, adding them up, and multiplying by 2. Okay, so let me do that. So I'll just take each of those guys, and multiply by 2. So what are they? There's 1, 2, 3 2's. 2, 3 2's. Let me go across the top. There's 3, 4, 6, 7. 3, 4, 6, 7, 8. Let me go across the bottom. Oh, there's 3 more 2's. Then a 3 and a 4. And let me go across the side again. Let me go down the side. There's an 8, 10, and a 7. Okay. So I just took these, I then added these, and then went down for added those. And then everything else, I don't know, maybe I'll put in purple or something. Everything else will be multiplied by 4. So all those other things, oh, I didn't mark the 2's. Not in the formula, I should have done that. I'll do that in a second. So then these are the 4's, those guys. And then the other ones were the 2's, these guys. Okay. So let's do this. Ooh, I need another page. I won't need that much. So a 7, that was it for that. Okay, so plus 4 times all the middle guys. I'll do it this way. I'll go like this, this, this. So I'll do 3, 4, 7, 8, 10. Next row, 4, 6, 8, 10, 12. Next row, 3, 4, 5, 3, 4, 5, 6, 8. Okay. So I just add up all those. So this is 25 over 4. So this is 10, 16, 2. That's 10, 25, 34, 38, 40, 50, 60, 72. Okay, that is 10, 18, 28, 28, 36, 42, 50, 60, 72, 79, 80, 98. Okay, so the volume is approximately, so plug that into your calculator, 3,450 square feet. Cubic feet. That is the approximate volume of this. Let's do another example. Problem number 16. So here in this example, we're actually going to evaluate a double integral. And so let's do the following. Let's first integrate. with respect to x. So let's integrate this with respect to x. So the integral of x plus a constant squared is 1/3 x plus that constant cubed, evaluated from x equals 0 to x equals 1. Okay, so let's evaluate this. So this is equal to, well, let's plug in 1. And so I just get 1 plus y cubed minus plug in 0. Oops, the 1/3. 1/3. 1 plus y cubed minus plug in x equals 0, y cubed. So let's integrate this. So if I integrate this, I get, well, the integral of 1 plus y cubed will be 1/4. So this becomes 1/12. 1 plus y to the 4th. The integral of 1/3 y cubed is 1/12 y to the 4th. And let's evaluate this. Between 0 and 1. So let's plug in 1. So this is 1/12, 2 to the 4th, minus 1/12, 1 to the 4th, minus, plug in 0, 1/12, 1 to the 4th, minus 1/12, 0 to the 4th. So let's evaluate this. And so 2 to the 4th is 16. One to the 4th is 1. Minus 1 to the 4th is 1. Minus 0. So this is equal to 16, over 12. So this is equal to 14 over 12, or 7 over 6. And that is your answer. Okay. Let me do problem number 24. So let's evaluate this. And so, let's write this as the integral. Well, actually, maybe I'll put a 2 in there to make it look nicer. So this is 1/2 integral 0 to 1, integral 0 to 1 of x to y, x squared plus y squared to the 1/2 dy dx. Okay, so I want to integrate something, a constant times 2y times y squared, a constant plus y squared all to the 1/2. I'm integrating this with respect to y. And so this is equal to 1/2 integral 0 to 1. I have here a constant, x, times, well, add 1, so this will be a 2/3 x squared plus y squared to the 3/2. And I'm integrating this from y equaling 0, y equaling 1. Okay, so this is equal to 1/2 integral 0 to 1. So I'll plug in 1. So this is 2/3 x squared plus 1 to the 3/2 minus 2/3 x x squared plus 0 squared, so that's just x squared. The 3/2 is x cubed dx. Okay, so let's integrate this. Oh, times your x. Sorry. So this is x cubed times 2/3 x is 2/3 x to the 4th. Okay, so this is, let's integrate this. And so this is equal to, I have here 1/2 and 1/3. Then I have a 2x, so let's just keep the 2 with the x. X squared plus 1 to the 3/2. So if I integrate that, that'll be, add 1 to that, gives you 2/5 x squared plus 1 to the 5/2 minus 1/3. I can just cancel the 2's. 1/5 x to the 5th. And this is evaluated between 0 and 1. Okay, so this is equal to, the 2's cancel, so that's 1/15. Plug in 1. So that's 2. Okay, let's say 2 to the 5/2 minus 1/15, 1 to the 5th. Okay. Minus, plugging in 0, 1/15. Again, plugging in 1. Plugging in 0. Sorry, I'm plugging in 0. That'll be 1 to the 5/2. Minus 0, so that doesn't give me anything. So this is equal to 1/15, so that's 4 rad 2 over 15 minus 1/15 minus 1/15 is 2/15. So this is equal to 2/15 times 2 rad 2 minus 1. And that is your answer. Okay. In problems 27 through 34, calculate the double integral. Okay, so I want to, in problem 28, I want to find the double integral over the region R, the rectangle R actually, in this case. So the region in this case is rectangle, of y plus x, y is negative 2 dA. So let's rewrite this. So this is equal to, it doesn't really matter which way. I'll just guess I'll do x and y, doesn't really matter. Integral 1 to 2, integral 0 to 2 of y plus x, y then negative 2. So 0 to 2 is x, so I write a dx. So notice that this integral involves the dx, and my limits of integration are my limits of integration for x. And then I'll do the dy. So I'll first integrate with respect to x, or with respect to y. And in this case, it really doesn't seem, in some cases, it could be easier to integrate in one order as compared to the other order. But in this case, I don't think it's really going to make a gigantic difference integrating either way. So first, let's integrate with respect to x. So the integral of a constant is just that constant times x. The integral of x is 1/2 x squared. And we're integrating between x equals 0 and x equals 2. So this is equal to integral 1 to 2. I'll plug in a 2, so it gives me a 2y plus 1/2 2 squared y to the negative 2 minus, well, plug in 0, and you're going to get 0. For both of these, you're just going to get 0, so that's not going to make any difference. Okay, dy. And so this is equal to, actually, let me write this as the integral from 1 to 2 of 2y plus 2y to the negative 2 dy. Since 4 divided by 2 is 2. So now let me integrate this. Let me give another page. Okay, so the integral of 2y is just y squared. The integral of 2 to the of y to the negative 2 is going to be a minus y to the negative 1. I'm integrating between 1 and 2. Okay, so let's plug in. So I get 2 squared minus 2 divided by 2, so that'll just be a 1. Plugging in 1, I get 1 squared minus 2. And so I get 4 minus 1 plus 2. And so my answer is 4. So integrating that double integral gave me a value of 4. Let me do problem number 42. Don't know if I have enough room. Let's just check to see if I do. I can probably take that next guy and bring it up. So I just sort of, since I drew the picture, I'm just going to, and I like sort of the picture, I'm just going to tag it along. Okay. And let me bring up my other one. Okay. So now let me read this off. Problem number 42. Find the volume of the solid in the first quadrant. So I want this to be in the first quadrant, octant, in the first octant. And so I want this to be in the first octant. So it's in this region here. Bounded by the cylinder. So I have this this cylinder here. Z equaling 16 minus x squared. So this is a circle of radius 4 centered along the z-axis, the y-axis. Okay, and so it looks something like this. And the plane 5. So it's only in the first octant. So that means that it's only going to be a quarter of the cylinder. And it starts here in the x z plane, and it ends when x is equal to 5. So it looks something like this. So if I look here at the bottom, I don't know if I can do this, but let's see. That's going to be a little big. Okay, so it's this region here. That doesn't look too bad. Is my R. Okay, there. So that's my R. So let me just draw that. So this has a radius of 4, since the circle here, the bottom of my cylinder, whatever you want to call it, the bottom or top of my cylinder has a radius of 4. And so this is at 4. And it goes all the way to y equaling 5. So the little r here is, okay. So now let's find the volume of this piece of a cylinder. So the volume is going to be, well, let's figure out what we're integrating order. Again, it may be easier to write in one as compared to the others, but it doesn't matter in this case. Let's do y and x. Okay. Well, if I look here at every little part of my region, I can put a little like rectangle. The little volume of that will be, well, whatever the height is of that tube, which in this case is going to be z, 16 minus y squared, x squared, sorry, 16 minus x squared, times the area, dA. But I've written it in terms of, well, x and y. I did, let's see, x first, and then y. So notice that this 0 to 4 is what x varies, and then for the y, well, it's 0 to 5. Okay, so let's integrate this. So this is equal to the integral from 0 to 5 of integrating respect to x. I'll get 16x minus 1/3 x cubed. And I'm evaluating this from x equaling 0 to x equaling 4. Okay, so let's plug in 4. So I get 16 times 4 minus 1/3 times 4 cubed minus the value at 0, but plugging in x equals 0 just gives me 0. So I don't have to subtract anything. And so 16 times 4 is 64. 4 cubed is 64. So one of these 64s minus a third of the 64s is 2/3 of 64. Maybe I'll write that as 128 over 3. And now let's integrate this. Well, this is equal to the integral of a constant, 123 over 8. 128 over 3 is just 128 over 3y. Integrated between 0 and 5. Well, if you plug in 5, you'll get 640 over 3 minus the value at 0, which is 0. And so your answer is 640 over 3. Okay. Let me do an example. Let f of x y equal 1 over y squared if 0 is between x, if 0 is less than x is less than y is less than 1, it is equal to negative 1 over x squared if y is 0 is less than y is less than x is less than 1, and it's 0 otherwise. So in all the other cases, in this case, we're actually going to restrict our definition to just looking at the unit square. But, and so in this, so otherwise it'll be 0. Show that the iterated integral from 0 to 1 for both x and y of f of x, where the order is dx dy, is not the same as the integral from 0 to 1 of f of x y dy dx. So this is an example where the order of the iteration actually gives you an incorrect answer. So let's do this. So first, let's suppose y is between 0 and 1. Okay. Then I have the following. The integral from 0 to 1 of f of x y dx. This will equal. So in this case, I'm fixing my y here. So I'm going to fix my y, and I'm integrating for x. Okay, so if I integrate for x, well, in this case, x goes from is between 0 and y. When x is between 0 and y, it's just 1 over y squared. So for x between 0 and y, how can you tell the order? Oh, so if they don't, so the answer is if they don't tell you, then it does not, then usually it won't really matter And so the question is, well, how do I know that I should have done, that I did X and Y? The answer is, in this case, it doesn't matter. You'll actually get the same answer. And it's just that, well, so how do you figure out the order? If you can do it, you do it. If it gives you something that's difficult, and you say, oh, this is a difficult integral, try the other way. So if it works, it works. If it doesn't work, try something else, is the answer. Okay? Now, of course, you have to be sure that all the conditions hold for Fubini's theorem. So if Fubini's theorem holds, then the order doesn't matter. But you have to be sure that Fubini's theorem holds. Okay, so let's do this. And so this is equal to the integral. X goes from 0 to y. So I see here that x goes from 0 to y. And between 0 and y, it's 1 over y squared, which is a constant. Now, if what does x go here? For here, x goes between y and 1. So for x going between y and 1, it's equal to negative 1 over x squared dx. Okay. So now let's integrate this. And so the integral of a constant is just, well, x over that x times the constant between x equaling 0, x equaling y. A lot of times, if there's more than one variable, and you don't know what you're plugging in, we always write down what the variable is we're substituting. Otherwise, it is a common mistake to plug in the wrong thing. So notice I'm integrating with respect to x, so I write x equal these limits. That'll prevent many unfortunate errors. Okay, so plus the integral of negative 1 over x squared, so that's x and negative 2, will just be a 1 over x between 1 and y. Well, in this case, it doesn't matter, but because there's no variable here. So, well, maybe I'll put in x just in case. Just so that we get into the good habit of always writing that. Let me do this. Okay, so this is equal to plug in y, so that's a 1 over y, minus 0. If you plug in x equals 0, you get 0, plus. Plug in 1, you get a 1. Plug in y, you get minus 1 over y. And so, integrating, I get a 1. So, I have the integral from 0 to 1 of f of x, y, dx, dy, is equal to the integral from 0 to 1. Well, we already integrated the one of f of x, y, dx. I found it was equal to 1. So let's finish the integration. So this is just, integral is just y between 0 and 1. You can put y equals 0, y equals 1. In this case, there are no other variables around, so I'm not going to get confused. Maybe I'll make it look like that. Okay. And so plug in 1, you get 1. Okay, good. So going one way, I get 1. Let's do the other way. So now, let's figure out what happens when y is between 0 and 1. Then 1 of f of x, y, dy. We already integrated first with respect to x. So now let's integrate with respect to y. And so, let me look for 1 second. So this is going to equal some integral. And so we're doing y. Okay. Okay, so y here. Let's do this one here. So if I look at y, y here goes from 0 to x. Well, when y goes from 0 to x, it's negative 1 over x squared. 0 to x. It's negative 1 over x squared dy. Plus, do the other integral. So now, I'm integrating with respect to y. And so y goes from x to 1. When y goes from x to 1, it's 1 over y squared. So 1 over y squared. From x to 1, it's 1 over y squared dy. Okay, so let's do this. So this is equal to integrating constant is just y times the constant between y equals 0 and y equal x. Let's integrate 1 over y squared, so it's y to the negative 2. So it'll be a negative 1 over y between y equal x, y equal 1. Okay. So now let's plug in. So this is equal to x over x squared. So that's a 1 over x. Plug in 0, so you get 0. Minus, plug in 1, you're just going to get a 1. Minus, and a minus make that a plus, 1 over x. So the 1 over x's cancel. And so I just get negative 1. Okay, so now let's finish up the integration. I should have, it will look, oh darn. Would look nicer doing it this way. Okay, so now let's do the integration. So I did y first. So let's do it the other way. So x okay, so this is equal to integral from 0 to 1. Well, we found that this integral is just negative 1 times dx. So this is a negative x between 0 and 1. Let me just pull this down a little bit. So I have some more room here. So this is just equal to a negative 1 minus 0 gives me a negative 1. But notice that when I integrate it, 0 to 1, f of xy dx dy, I got that this was a plus 1. And when I integrated the other way, so you must be sure that the conditions for this is equal to -1. So they're not equal. 1 is not equal to -1. And so in order for you to switch the order of integration when you're doing iterated integrals, be sure that all the conditions for Fubini's theorem hold. Otherwise, what you're doing could be incorrect. Okay, you always have to check all conditions hold. If not, you could be in trouble. Okay, so actually, why is this going up so high? Let f of xy equal x cubed over y squared e to the negative x squared over y if y is greater than 0, and 0 if y is equal to 0. Show that the derivative of the integral from 0 to 1 of f of xy dy is not the same as just putting the integral, switching the order between, well, integration and differentiation. This is not the same as the integral from 0 to 1 of the partial of f with respect to x dy. So show that these two things are not the same. Okay, so let's do that. Okay, so first, let's try to integrate f dy. So let's integrate this. Okay, well, so f of xy is just equal to this quantity here for y greater than 0. So because of that, and we're integrating, it doesn't matter what happens when y equals 0. That's a set of measures 0. So this is just the integral. From 0 to 1 of x cubed over y squared e to the negative x squared over y dy. So let's look at this first, and then after I've simplified this, I'll differentiate it. Okay, so this is equal to, well, the integral of x squared over y squared e to the negative x squared over y is just e to the negative x squared over y. And so this integral here is just x e to the negative x squared over y. And I'm evaluating between y equals 0 and y equals 1. Okay? And so let's plug in. Okay, here. So let's just plug in. So if I plug in y equal 1, I just get x e to the minus x squared. If I plug in y equals 0, oh. Wait once. Okay. So if I plug in y equals 0, well, obviously I can't plug in 0. But if I do the limit as y approaches 0, of x, maybe I'll write it here, x e to the minus x squared over y, okay, so x, so I have here a negative number, and this is going to negative, so negative x squared, negative x squared over y, that approaches negative infinity, so e to negative infinity goes to 0. So this whole term here just goes off to 0. Okay, so this is equal to x e to the minus x squared. Okay. Okay, so now let's take the derivative. So the derivative of the integral from 0 to 1 of f of xy dy. So this is just equal to the derivative of x e to the minus x squared. So let's use the product rule. So it's the derivative of the first times the second plus the first times the derivative of the second. Well, the derivative of e to the exponent is e to that exponent times the derivative of the exponent. And so, oops, this is just equal to 1 minus 2x squared e to the minus x squared. Okay. And so, if I actually look at this when x equals 0, so let's look at the derivative of this integral. When x equals 0. Well, this is just going to, if I plug in 0 here, that's just going to be a 1. This is going to be 0, so 1 minus 0 is 1 times 1 is 1. So I get that this whole thing is equal to 1. Okay. Next, let's look, well, the integral from 0 to 1 of the partial of f with respect to x. This is going to equal well, let's take the partial with respect to x. So again, let's use the product rule, Leibniz rule. So the derivative of the first, 3x squared over y squared. So it's 3x squared over y squared times the second, e to the minus x squared over y plus the first, x cubed over y squared times the derivative of the second. Derivative of e to any exponent is e to that exponent times the derivative of the exponent, negative 2x over y dy. Okay, so that's the partial derivative. Okay, so now let's, maybe I'll try to simplify that somewhat. And so, this is equal to and let's evaluate this when x equals 0. So, when x equals 0, we have the following. So, this is a 0, and this term will be 0. So all this stuff inside is just going to be 0 when x equals 0. So this is equal to the integral from 0 to 1 of this partial is the integral from 0 to 1 of 0. And so if you integrate that, you'll get 0. But so therefore, I have the derivative from 0 to 1 of f of x, y, dy, evaluated at x equals 0, is not the same as the integral from 0 to 1, the partial of f with respect to x at 0y dy. And that's what I wanted to show. So that finishes off section 15.1